Far above the civilized world sits the North Pole, a solitary point drifting endlessly on a frozen ocean. It is a place of perpetual motion disguised as stillness. Unlike the South Pole, which rests on a massive continent of rock and earth, the North Pole is not on land at all. As you settle in, perhaps gently clicking the subscribe button to join us for future quiet explorations, consider the water waiting beneath the ice. The geographic North Pole, located at exactly 90 degrees north, sits squarely in the middle of the Arctic Ocean. Here, the water is approximately 4,000 meters deep, or just over 13,000 feet, leading down into the dark abyss of the Amundsen Basin. There is no bedrock here to anchor a flag. Instead, the pole exists on a shifting crust of sea ice, usually only 2 to 3 meters thick. This creates a strange reality for anyone who visits. If you were to stand at the precise top of the world, you would constantly be moving. The ice flows are driven by the transpolar drift stream, traveling several miles every single day. An explorer who pitches a tent at 90 degrees north will wake up the next morning having drifted far from the pole, requiring them to pack up and ski back to the coordinate just to say they are still there. This distinction defines the Arctic. While Antarctica is a continent surrounded by an ocean, the Arctic is an ocean surrounded by continents. This geography allows the warmer ocean currents from the Atlantic to flow beneath the ice, moderating the temperatures slightly compared to the brutal extremes of the Antarctic interior. Yet, the isolation here is absolute. The nearest land is usually the precarious northern edge of Greenland, hundreds of miles away across the jagged pack ice. At this singular point, the fundamental rules of navigation dissolve. Everywhere you look is south. East and west cease to exist, as all lines of longitude converge beneath your feet. Because time zones are defined by these longitude lines, the North Pole technically occupies every time zone simultaneously. With no local settlements to dictate the hour, human time becomes arbitrary here, often defaulting to Greenwich Mean Time or simply the time zone of the country from which the traveler departed. While the hands of a clock may lose their meaning at this convergence of longitudes, the physical world beneath the ice is defined by concrete, measurable immensity. If you could strip away the shifting skin of sea ice and gaze directly downward, you would be looking into a watery chasm more than 2.5 miles deep. The North Pole is not situated on land, nor even on a typical continental shelf, but rather floats over a dramatic and complex underwater landscape known as the Arctic Basin. Dominating this hidden topography is the Lomonosov Ridge. This is an unusual underwater mountain chain that runs right through the heart of the Arctic Ocean, spanning roughly 1,100 miles from the New Siberian Islands toward Greenland and Ellesmere Island. The geographic North Pole is located relatively close to this ridge, hovering over the slopes that descend into the abyss. Geologically, this ridge is fascinating because it is not formed by volcanic spreading like the Mid-Atlantic Ridge. Instead, it is a sliver of continental crust that was torn away from the edge of the Eurasian continent roughly 64 million years ago. It is a drowned piece of the mainland, a phantom continent submerged in the dark. This ridge acts as a massive partition wall, dividing the deep Arctic into 2 major basins. On the Canadian side lies the Makarov Basin, and on the Eurasian side sits the Amundsen Basin. The North Pole is technically positioned over the Amundsen Basin, just off the flank of the ridge. In 2007, a Russian submersible mission famously planted a titanium flag on the seabed here, recording a depth of 4,261 meters. That is nearly 14,000 feet of water, a vertical column so massive it crushes any conventional concept of space. Down in the benthic zone, the environment is defined by stillness and weight. The hydrostatic pressure at the bottom exerts a force of over 6,000 pounds per square inch. This is roughly 400 times the atmospheric pressure you feel standing at sea level. In this high-pressure environment, water behaves differently, and despite the temperature hovering around negative 0.8 degrees Celsius, the salt water does not freeze. It remains a supercooled liquid, slightly denser than the water above it. The floor itself is a flat, silent plain of soft clay and silt. Because the Arctic is an enclosed ocean surrounded by continents that drain their rivers northwards, fine sediment has been settling here for millions of years. This accumulation is incredibly slow, creating a thick blanket of mud that records the planet's climatic history in microscopic layers. Unlike the turbulent surface where ice crashes and winds howl, the bottom of the pole is one of the quietest places on Earth. There are no strong currents to scour the bottom. The deep water here is isolated by the walls of the Lomonosov Ridge, preventing it from mixing freely with the Canadian side of the basin. It sits in the dark, unaffected by the storms raging miles above. As we move upward from these depths to meet the frigid air at the surface, we encounter a boundary where the laws of thermodynamics construct a solid world out of liquid chaos. The formation of sea ice in the Arctic is a far more complex physical process than the freezing of a freshwater pond. In a simple lake, water molecules lock into a hexagonal lattice at 0 degrees Celsius. But the Arctic Ocean is teeming with dissolved salts, sodium, chloride, and magnesium, which act as stubborn intruders. These ions hustle between the water molecules, physically preventing them from bonding. Consequently, the ocean's surface must cool significantly further, down to roughly minus 1.8 degrees Celsius, before the phase change can finally overpower the chemical interference. When the ice finally begins to crystallize, it remains a purist. The crystal lattice of water ice is incredibly selective and has no room for salt within its geometry. As the water freezes, it actively pushes the salt ions out, a process oceanographers call brine rejection. This expulsion concentrates the salt into tiny brine-filled pockets and channels trapped between the pure ice crystals. Eventually, this hypersaline water becomes so dense and heavy that it drains out of the ice entirely, plunging rapidly into the dark water below. This means that multi-year sea ice, having drained its brine over time, is nearly fresh enough to drink, physically distinct from the salty water from which it was born. The visual evolution of this freezing process is hypnotic. It starts with phrasal ice, tiny needle-like crystals that shimmer in the water like suspended diamond dust. As these crystals multiply, they do not immediately form a hard sheet. Instead, the ocean's surface takes on a dull, oily appearance known as grease ice. It behaves like a thick, viscous soup, sluggishly rolling with the waves. If the water is calm, this slush coagulates into a dark, elastic crust called nylase, which is flexible enough to bend over the ocean swells without snapping. However, if the seas are rough, the waves bump the forming ice into slushy circular disks known as pancake ice. As these disks collide repeatedly in the chop, their edges are hammered up into raised rims, creating a vast field of white lily pads floating on the black water. Regardless of its shape, as the ice thickens and consolidates into a continuous pack, it performs a massive mechanical service. It silences the ocean. The flexibility of the ice sheet absorbs the kinetic energy of the waves. A rolling ocean swell that enters the ice pack is quickly dampened, its energy drained by friction against the rough underside of the ice. This creates a profound acoustic shift. The relentless roar of breaking whitecaps and the hiss of sea spray are physically suppressed, capped by the lid of the cryosphere. The result is a soundscape of immense stillness, where the ocean's energy is hidden beneath a floor that gently rises and falls, breathing in a slow, silent rhythm. Yet, if you were to stand perfectly still on that breathing floor, fixing your position at exactly 90 degrees north, you would not stay there for long. The geographic North Pole is a fixed mathematical point, the precise intersection where all lines of longitude converge, but the physical landscape that occupies that spot is transient. The ice beneath your feet is merely passing through. It is a restless skin, constantly sliding over the surface of the dark ocean below, driven by a powerful conveyor belt known as the transpolar drift stream. This massive current is one of the primary circulation systems of the Arctic Ocean. It acts as a river of ice, born in the shallow, freezing waters off the coast of Siberia. Here, in the Laptev and East Siberian seas, the relentless cold of the polar winter generates new sea ice at a staggering rate. Once formed, this ice does not remain stagnant. Pushed by prevailing wind patterns and the rotation of the Earth, it is herded northward, beginning a journey that spans thousands of miles. The ice flows travel across the pole itself, eventually funneling out into the North Atlantic through the deep channel between Greenland and the Svalbard archipelago, known as the Fram Strait. The speed of this transit is deceptive. To the naked eye, the horizon looks motionless, but in the context of geology, it is racing. A research camp established directly on the geographic pole can drift anywhere from 1 to 4 miles in a single 24-hour period. Scientists working in these high latitudes often speak of the strange sensation of going to sleep at the top of the world, only to wake up significantly south of it, their entire station having been carried away by the drift while they dreamed. To remain at the true pole requires a constant northward hike, walking endlessly against the current like someone trying to ascend a down escalator that never stops. Long before satellite telemetry could track these shifting plates, the existence of this great drift was revealed by the ocean itself, through the silent testimony of driftwood. Indigenous Greenlanders, living far beyond the tree line where the climate is too harsh for forests to grow, relied for centuries on timber that mysteriously washed up on their frozen shores. When botanists eventually examined these logs, they discovered a biological anomaly. The wood was not from North America or Scandinavia, it was Siberian larch. These trees had fallen into rivers deep in the heart of Russia, floated out to the Arctic coast, and become frozen into the pack ice. They were then carried over the very top of the world, a journey taking several years before finally being released during the summer thaw near Greenland. It was this realization that inspired the explorer Fridtjof Nansen to intentionally freeze his ship, the Fram, in 1893, proving that a vessel could ride the drift across the polar basin. However, this global migration of ice is rarely a peaceful glide. As the transpolar drift stream shoves millions of square miles of frozen ocean against the coastlines and narrow straits, the immense pressure creates a landscape of tension. The ice is not a solid, unbroken continent, but a jigsaw puzzle of tectonic forces, where the stress of movement tears the surface apart. When this tearing occurs, deep fractures appear in the white crust, revealing the jet-black ocean beneath. These linear cracks are known as leads. They cut across the frozen landscape like rivers of dark ink, sometimes stretching for miles in jagged, unpredictable lines. Unlike a canyon on land, a lead is transient and alive. It opens when the ice flows diverge, drifting apart under the influence of shifting currents or changing winds. But just as quickly as they open, they can slam shut. When the drift reverses, the two sides of the lead collide with tremendous force, sending slabs of ice rafting over one another or building vertical ridges that block the path of any surface traveler. While leads are temporary fractures, there exists a more stable and mysterious phenomenon known as the polynya. Derived from a Russian word referring to a hollow or a pool, a polynya is a substantial area of open water that remains unfrozen even in the dead of the polar winter. In an environment where the air temperature plunges to 40 degrees below zero, the persistence of liquid water seems to defy the laws of nature. Yet it is a strict matter of thermodynamics. These open windows are maintained by two primary engines. The first is wind. In coastal polynyas, fierce gales blow off the land or ice shelves, physically shoving the newly formed ice out to sea as rapidly as it creates itself. This turns the polynya into a massive ice factory, constantly freezing water that is immediately exported, leaving the surface clear. The second mechanism is driven by the ocean's own internal heat. These are open ocean polynyas, created when relatively warm water from the deep is forced to the surface. This process, known as upwelling, acts like a localized heater. The rising water carries enough thermal energy to melt the ice from below, preventing a solid lid from forming despite the freezing atmosphere. Whether formed by wind or heat, these openings serve a critical role as the breathing holes of the Arctic. Without the insulating blanket of ice, the exposed water releases immense amounts of heat and moisture into the dry polar air, creating towering columns of condensation, often called sea smoke. For the marine life of the North, these areas are not merely thermodynamic curiosities, but vital oases. They provide the only reliable access to air for air-breathing mammals like narwhals and bowhead whales, allowing them to navigate deep into the ice pack without suffocating beneath the shifting frozen ceiling. While these animals rely on instinct and acoustics to navigate the darkness, humanity has long relied on a different invisible guide. We look to the compass, assuming the needle points to the top of the world. Yet the North Pole that a compass seeks is not the same as the North Pole found on a standard map. We often conflate the two, imagining the Arctic centers around a singular fixed pin in the globe. In reality, there is a profound distinction between the geographic North Pole and the magnetic North Pole. The geographic North Pole, also known as true north, is a geometric certainty. It is the precise point where the Earth's axis of rotation intersects the surface. It is located at 90 degrees north latitude, sitting near the center of the Arctic Ocean. Here, all lines of longitude converge to a single mathematical dot. It is the point around which the planet spins, and relative to the bedrock of the Earth, it remains effectively static. If you were to plant a flag at true north, it would remain at the axis of rotation as the ice drifted beneath it. Distinct from this fixed anchor is the magnetic North Pole. This is a wandering, restless location that refuses to stay put. The existence of this second pole is a direct result of the violent, churning geophysics happening deep beneath the ice, far below the crust. Approximately 3,000 kilometers down sits the Earth's outer core. This is a vast ocean of molten iron and nickel, roughly as fluid as the water on the surface, but intensely hot and under crushing pressure. As heat escapes from the solid inner core, this molten iron churns in massive convection currents. Because the Earth is spinning, these currents are twisted by the Coriolis force, creating spiraling columns of conductive fluid. This complex movement turns the planet into a massive, self-sustaining electromagnet, a process known as the geodynamo. It generates the magnetosphere that shields us from solar radiation. But because this dynamo is driven by liquid turbulence rather than solid rock, the field it creates is never perfectly stable. Consequently, the point on the surface where that magnetic force is strongest, the magnetic North Pole, is constantly in motion. It is a ghost that haunts the high Arctic, drifting comfortably across political borders and open oceans. For centuries, this magnetic point lingered within the scattered islands of the Canadian Arctic. When explorer James Clark Ross first pinned it down in 1831, it was located on the Boothia Peninsula in Nunavut. Back then, it was a sluggish traveler. For much of the 20th century, it drifted at a leisurely pace of perhaps 10 kilometers a year. However, in the 1990s, something deep within the core changed. The magnetic pole began to sprint. Its speed jumped to over 50 kilometers a year, racing across the Arctic Ocean, leaving the Canadian archipelago behind and heading decidedly toward Siberia. Geophysicists believe this sudden acceleration is caused by a subterranean rivalry. There are two main patches of magnetic intensity near the core mantle boundary, one beneath Canada and one beneath Siberia. For a long time, the Canadian patch was stronger, effectively holding the pole in place. Recently, that hold has weakened, and the Siberian patch is winning the tug-of-war, pulling the pole across the international dateline. This movement is so rapid and significant that organizations like the British Geological Survey and NOAA have had to issue emergency updates to the World Magnetic Map, the mathematical map that underlies GPS systems and navigation tools in everything from smartphones to military submarines. There is also a fascinating geometric quirk to this wandering location. If you were to stand precisely on the magnetic North Pole and hold a standard compass, the needle would not know where to point. It would lose all horizontal direction and drift aimlessly. This is because the magnetic field lines here are curving inward, plunging vertically straight down into the Earth. On the equator, magnetic field lines run parallel to the ground, but at the pole, they are perpendicular. This is why scientists often refer to it as the dip pole. At this specific spot, the magnetic inclination is 90 degrees. A specialized dip circle compass would point straight at your feet, aligning with those invisible lines diving through the crust back toward the churning iron heart of the world. However, for a traveler holding a standard hiking compass, this vertical pull creates a functional crisis. Most compass needles are balanced on a delicate pin, designed to rotate freely on a horizontal plane. But as you enter the high Arctic, the magnetic force pulling downward becomes significantly stronger than the force pulling northward. This creates a phenomenon known as dip error. The north-seeking end of the needle tries to dive toward the Earth, dragging against the compass housing. The friction locks the needle in place, making it sluggish or entirely unresponsive. Even if you have a compass balanced for high latitudes, the horizontal magnetic force is so weak near the pole that it can hardly overcome the friction of the pivot. The needle drifts aimlessly. Navigators and scientists refer to this frustrating zone as the sphere of confusion. It is not a small specific point, but a vast area surrounding the magnetic pole where directional readings become erratic and essentially useless. Depending on the strength of the magnetic field at the time, this sphere of confusion can extend for hundreds of miles, creating a blind spot where the cardinal directions seem to dissolve. Have you ever tried to navigate the old-fashioned way? Perhaps on a camping trip using only a paper map and a simple magnetic compass. It is a distinct type of focus, relying on geometry and trust in a small floating needle, a skill that feels increasingly rare in a world of digital positioning. For the explorers of the 19th and early 20th centuries, entering this magnetic blind spot was terrifying. Before the advent of satellite navigation, they relied heavily on dead reckoning and celestial observations. But the Arctic environment conspires against these methods. The sun often stays low on the horizon for long periods or disappears entirely during the winter, while summer brings thick, persistent fogs that obscure the sky. Without the sun for a sextant reading, and without a reliable compass for orientation, early adventurers were often walking blind. To make matters worse, they were traversing sea ice that was constantly drifting. A team could march 10 miles north in a day, but if the ice beneath them drifted 10 miles south, they would wake up in the exact same geographic position, with no magnetic needle to tell them they had gone off course. It is also worth noting that the Earth's magnetism does not behave with perfect symmetry. You might assume that the North Magnetic Pole has a twin directly on the opposite side of the globe, but geomagnetism is rarely so tidy. The South Magnetic Pole is currently located just off the coast of Antarctica, but it is not antipodal to the North Magnetic Pole. If you were to draw a straight line through the center of the Earth starting from the North Magnetic, you would miss the South Magnetic by a significant distance. The two poles wander independently, driven by different eddies and currents in the planet's molten outer core, dancing to their own individual rhythms. This invisible choreography sets the stage for the most famous byproduct of our magnetic shield, the aurora borealis. While the poles themselves are silent wanderers, they act as the funnel for a chaotic stream of energy originating 93 million miles away. The sun does not merely shine light upon us, it constantly exhales a breath of charged particles known as the solar wind. This plasma, a soup of protons and electrons, races across the solar system at speeds exceeding 1 million miles per hour, eventually slamming into Earth's magnetic field. If our planet did not have this magnetic dynamism generated by the core, the solar wind would strip away our atmosphere, leaving the surface barren. Instead, the magnetosphere intercepts this barrage. It compresses on the sun-facing side and stretches out into a long, trembling tail on the night side. Under normal conditions, the magnetic field deflects most of these particles, but the shield is not impermeable. At the polar cusps, funnel-like openings near the magnetic poles, and during periods of intense solar activity, the charged particles are captured. They spiral inward, accelerating along the invisible magnetic field lines until they collide with the gases in our upper atmosphere. The result is effectively a celestial neon sign. The physics are identical. Electricity excites gas atoms, causing them to light up. However, the specific colors detailed in auroral displays are strictly dictated by the chemical composition of the atmosphere and the altitude of the collision. The most common color, a ghostly pale green, is produced by oxygen molecules located about 60 to 150 miles above the ground. Our eyes are highly sensitive to this green wavelength, making it the dominant feature in most photographs and sightings. Rarely, the aurora creates a blood-red hue. This too is caused by oxygen, but it occurs at much higher altitudes, often exceeding 200 miles. At this height, the atmosphere is extremely thin, allowing excited oxygen atoms enough time to emit a red photon before colliding with another atom. Lower down, collisions happen too frequently, quenching the red light before it can form. When the solar wind is particularly energetic, it can penetrate deeper into the atmosphere, below the 60-mile mark, where it strikes nitrogen molecules. This interaction yields the beautiful, rapid flashes of purple, violet, and pink that often fringe the lower edges of the auroral curtains. Contrary to common illustrations that place the northern lights directly atop the geographic North Pole, the phenomenon actually occurs in a ring known as the auroral oval. This halo creates a band around the geomagnetic pole, usually spanning latitudes between 60 and 75 degrees. Consequently, if you were standing at the exact geographic North Pole during a moderate solar storm, you would likely look south to see the lights, rather than straight up. The oval is not static. During intense geomagnetic storms, the ring widens and thickens, pushing the lights further toward the equator and allowing observers in lower latitudes to witness the spectacle. Perhaps the most surreal aspect of these ribbons of light is their silence. We are accustomed to associating massive energy releases, thunderstorms, explosions, roaring fires with immense sound. Watching the sky tear open with undulating curtains of green and violet fire, the human brain instinctively expects a crackle, a hiss, or a roar. Yet, the show is typically completely silent. The collisions occur in a near vacuum where the air is far too thin to carry audible sound waves down to the surface. Reports of hissing auroras are often attributed to psychoacoustic effects or local electrical discharges on the ground, rather than sound traveling from the upper atmosphere. However, the aurora is loud in a different spectrum. It emits a cacophony of radio waves, whistling and chirping in frequencies that our ears cannot perceive, but which radio receivers pick up as a chaotic alien chorus. Visually, the lights appear to fold and ripple like heavy drapery moving in a slow breeze. The sun breaches the horizon in March. It does not set again until September. This is the midnight sun. Because of the axial tilt, the sun appears to move in a horizontal circle, hovering roughly the same distance above the horizon at midnight as it does at noon. It simply rotates around you, never dipping below the edge of the world to offer a moment of respite. This relentless illumination creates a fascinating conflict for biological life. Most organisms on Earth evolved under the rhythmic pulse of the circadian cycle, the roughly 24-hour loop of light and dark that synchronizes internal clocks. In the high Arctic, that external signal, known as a Zeitgeber, vanishes for months at a time. Reindeer, for instance, have been found to suppress their circadian rhythms during these periods to feed whenever conditions allow. For human physiology, however, the adjustment is difficult. The absence of darkness confuses the hypothalamus, specifically the suprachiasmatic nucleus, which regulates melatonin. Without the trigger of night, the body struggles to recognize the biochemical signal for sleep, leaving the internal clock drifting in a sea of constant light. But that sea of light does more than confuse the internal clock. It actively distorts the physical world through a series of atmospheric optical illusions that are almost unique to the polar regions. In the high Arctic, the air often acts as a massive, complex lens, bending reality in ways that can baffle even seasoned observers. This begins with the phenomenon known as the Fata Morgana. While common mirages in hot deserts are caused by heated air near the ground refracting light upward, the Arctic mirage works in reverse due to a temperature inversion. Here, a layer of cold, dense air sits directly on top of the ice, while warmer air rests above it. Because light travels slower through the denser cold air, rays passing through these layers are bent toward the Earth. This atmospheric refraction creates a ducting effect, allowing an observer to see objects that are actually located well beyond the horizon. The image is not just displaced, it is vertically stretched and distorted. An unremarkable strip of flat sea ice might appear as a towering cliff face or a majestic mountain range, leading early explorers to chart islands and landmasses that simply did not exist. This illusory topography, composed entirely of bent light, has appeared on maps for centuries, only to vanish when expeditions ventured closer. The visual deception continues with the presence of diamond dust, or ground-level clouds composed of tiny ice crystals. When these crystals are shaped like hexagonal plates and drift slowly downward with their flat faces parallel to the ground, they act as millions of miniature prisms. As sunlight passes through the side faces of these hexagons, it is refracted by exactly 22 degrees. The result is the appearance of parhelia, commonly known as sundogs. These are bright, rainbow-colored spots of light that flank the actual sun on the left and right, often connected by a luminous halo. In the distinct stillness of the Arctic atmosphere, these phantom suns can sometimes appear nearly as bright as the sun itself, creating the unsettling sensation of a sky with three distinct light sources. When these same hexagonal plate crystals are suspended in the air above an artificial light source, or even the moon, they create light pillars. Instead of refracting through the crystal, light reflects off the bottom faces of the floating ice plates. Because the crystals wobble slightly as they fall, like leaves drifting from a tree, they reflect the light at various angles, creating a coherent vertical column that appears to beam directly upward into the night sky. Perhaps the most disorienting illusion of all is the Novaya Zemlya effect. Named after the Russian archipelago where it was first documented in 1597, this phenomenon allows the sun to be seen when it is geometrically below the horizon. During the deep polar twilight, strong temperature inversion layers can trap sunlight in an atmospheric duct, guiding the rays around the curvature of the Earth like a signal traveling through a fiber optic cable. This super-refraction can make the sun appear as a distorted, rectangular band of fire hovering on the horizon days before the polar night officially ends, mocking the precise calculations of astronomers. High above these optical illusions, the atmosphere itself is governed by a massive invisible engine known as the polar vortex. While the term frequently dominates winter news cycles, typically framed as a temporary storm system, it is actually a permanent feature of the Earth's climatology. Scientifically, the vortex is a large area of low pressure and cold air surrounding the pole, extending from the middle of the troposphere all the way up into the stratosphere. The term vortex refers specifically to the counterclockwise flow of air that helps keep the colder air concentrated near the polar cap. This circulation is driven by the rotation of the Earth and the stark temperature difference between the frozen Arctic and the warmer mid-latitudes. To understand why this system exists, we must look at the relationship between temperature and pressure. In the winter, the Arctic is shrouded in darkness, allowing the air to cool dramatically. This cold, dense air sinks, creating a low-pressure system at high altitudes. Surrounding this core of cold air is the polar jet stream, a ribbon of strong winds that races from west to east at speeds often exceeding 100 miles per hour. You might imagine the jet stream as a flexible fence or a dam. When the vortex is strong and stable, the jet stream flows in a relatively straight, tight circle, effectively trapping the frigid air at the top of the world. However, the atmosphere is rarely static. Occasionally, energy from the lower atmosphere moves upward and disrupts the stratospheric vortex in an event called a sudden stratospheric warming. During these episodes, the temperature in the stratosphere can jump by as much as 50 degrees Celsius in just a few days. This rapid warming causes the vortex to weaken, slow down, or even reverse direction. If we use the analogy of a spinning top, a strong vortex is a top spinning rapidly and staying in one place. A weak vortex is like a top that is losing speed. It begins to wobble and drift off its center. When this wobbling occurs, the fence of the jet stream develops deep meandering loops known as planetary waves. Instead of a tight circle, the winds dip far to the south. This breach allows the ultra-cold Arctic air to spill out of the polar region and descend into the mid-latitudes, bringing freezing temperatures like North America, Europe, and Asia. Paradoxically, a weak polar vortex results in severe winter weather for the populations living south of the Arctic Circle, while the North Pole itself might experience unusually mild temperatures during these disruptions due to the intrusion of warmer air from the south. It is important to distinguish between the vortex itself and the weather we feel on the ground. The true polar vortex lives in the stratosphere, some 10 to 30 miles above the surface. What we experience as a cold snap is usually the result of the jet stream distorting in the troposphere, the lowest layer of the atmosphere. While the two are linked, they operate on different scales. The air contained within this system is not only cold, but also exceptionally dry. Because cold air holds significantly less moisture than warm air, the atmosphere inside the vortex creates conditions that are surprisingly arid. This leads to a counterintuitive fact about the environment at the pole. Despite being covered in ice, the region receives very little fresh snow. Consequently, climatologists technically classify the high Arctic as a polar desert. While we typically associate deserts with scorching sand dunes, the scientific definition relies on precipitation levels rather than temperature. The area surrounding the geographic North Pole generally receives less than 10 inches of water equivalent per year, placing it in the same category as some of the driest regions of the Sahara. The air is simply too frozen to carry the heavy moisture loads required for frequent heavy snowstorms. Instead of thick blankets of fresh snow, precipitation often manifests as a delicate phenomenon known as diamond dust. This occurs when the air becomes so intensely cold that water vapor deposits directly into tiny ice crystals right near the ground, rather than falling from clouds high above. It is essentially a ground-level cloud composed of solid ice. These crystals are often shaped like perfect hexagonal plates or columns. Because they are so microscopic, they do not fall quickly. They drift, hanging in the air like a glittering suspended fog. When sunlight interacts with these floating prisms, it refracts to create sparkling halos, vertical light pillars, or sundogs, bright spots of light flanking the sun. The visual experience of this environment is further defined by the exceptional purity of the atmosphere. Being thousands of miles from major industrial centers and soil-covered landmasses, the polar air is nearly void of dust, soot, and pollen. This lack of particulate matter creates a startling clarity. Distant ridges of pressure ice might appear to be close enough to touch, yet sit miles away. Without atmospheric haze to provide the usual depth cues, the scale of the landscape becomes nearly impossible for the human eye to judge accurately. This optical confusion reaches its absolute peak during a whiteout. While often confused with a blizzard, a true whiteout is a specific condition of light. When a uniform layer of white clouds covers the sky and the ground is unbroken white ice, the light diffuses in every direction. Shadows vanish completely. The horizon line dissolves, blending the sky and earth into a seamless, featureless void where depth perception fails entirely. Yet, beneath these optical illusions, the weather patterns are often surprisingly stable. The region is dominated by high-pressure systems where cold, heavy air sinks toward the surface. This suppresses the turbulent vertical air currents that usually drive storms, resulting in long stretches of calm, clear, and profound silence. While the air above remains hushed under high pressure, the ice sheet itself serves as a profound acoustic insulator. A thick layer of dry snow on top of sea ice acts like a heavy, porous blanket, dampening the few sounds that do exist in the atmosphere. If you were standing on the surface, the wind might whisper across the drifts, but that snow absorbs the acoustic energy, preventing it from penetrating downward. However, once you cross the physical threshold into the water below, the rules of physics shift dramatically. In the dense medium of seawater, sound travels more than 4 times faster than it does in the air, moving at speeds exceeding 1,400 meters per second. In most of the world's oceans, the speed of sound is dictated by a complex balance of temperature and pressure, usually creating a deep path known as the SOFAR channel, where sound waves travel uninterrupted. In the high Arctic, however, the temperature profile is inverted. The water is coldest right near the surface, just beneath the ice. Because sound waves bend toward areas of slower velocity and sound travels slower in colder water, the acoustic energy in the Arctic is constantly refracted upward. The waves arc toward the surface, strike the underside of the rough ice, and reflect back down, only to curve upward again in a continuous cycle. This creates what oceanographers call a surface duct, or the Arctic half channel. This unique acoustic waveguide allows noise to travel for thousands of kilometers with very little loss of energy, effectively turning the entire ocean basin into a massive, highly efficient echo chamber. Consequently, the environment below the North Pole is surprisingly noisy, teeming with the sounds of geophysics rather than biology. The ice pack is a dynamic, shifting tectonic plate of frozen water. As the ice flows drift, driven by deep currents and the rotation of the Earth, they grind against one another. This mechanical stress creates a constant background cacophony known as the ambient noise field. When the temperature drops rapidly, the ice undergoes thermal contraction, leading to sudden sharp fractures. Acoustically, these events register as broad-spectrum noise. The grinding of shear ridges produces low-frequency groans and rumbles, often sitting below 100 Hz, that can resonate through the water column for hours. Conversely, the formation of thermal cracks creates high-frequency snaps, often described by hydrophone operators as sounding like popcorn or crackling knuckles. These impulsive sounds can reach immense source levels, sometimes exceeding 200 decibels relative to 1 micropascal, creating a sonic environment that fluctuates wildly in intensity. In the summer months, as the ice melts, the release of high-pressure air bubbles trapped within the glacier ice adds a continuous, high-frequency hiss to the water, adding yet another layer to this complex underwater soundscape. Beneath the surface noise of cracking ice and escaping air bubbles, a much deeper and slower event is taking place, one that acts as the silent heartbeat of the global ocean. Here, in the high latitudes of the North, the water is not merely a passive recipient of the cold, it is the active engine of a planetary current. This is the origin point of the global ocean conveyor belt, known formally to oceanographers as thermohaline circulation. The term itself offers the key to understanding the physics at play. Thermo referring to temperature and haline referring to salt content. These two properties determine the density of seawater, and nowhere is their interplay more critical or more powerful than at the poles. As the intense Arctic winter settles in, the surface of the ocean begins to freeze, but sea ice behaves differently than freshwater ice you might find in a domestic freezer. As salt water freezes into crystal structures, it rejects the majority of the salt ions held within it, forcing them out into the surrounding liquid. This process, known as brine rejection, leaves the water immediately beneath the ice incredibly salty. Simultaneously, the biting winds and sub-zero atmosphere cool this hypersaline water to near freezing temperatures. The result is a layer of surface water that is both frigid and dense with salt, making it significantly heavier than the warmer, fresher water sitting deeper in the column. Gravity inevitably takes over. This heavy surface water can no longer stay afloat. It begins to sink, plunging thousands of meters down toward the abyss in a process that powers the world's oceans. In the Greenland Sea, the Norwegian Sea, and the Labrador Sea, these sinking columns create massive, invisible waterfalls that dwarf any cascade found on land. Millions of cubic meters of water per second drop to the ocean floor, crashing into the bottom and spreading out. Because it is so dense, this water hugs the topography of the seabed, forming a distinct, coherent layer known as North Atlantic deep water. Once it reaches the bottom, this cold torrent begins a slow, relentless migration southward. It flows beneath the rest of the Atlantic Ocean, crossing the equator deep in the dark, heading all the way to Antarctica. This deep exit creates a massive vacuum at the surface of the Arctic. To replace the water that sank, warm surface water from the tropics is pulled northward. This is the hydraulic mechanism that drags warm currents like the Gulf Stream toward the Arctic, transporting vast amounts of heat from the equator to the high latitudes. The North Pole, in essence, acts as the planet's cooling system, while the currents it drives act as the plumbing that redistributes solar energy, keeping the tropics from overheating and the northern latitudes from freezing entirely. The most staggering aspect of this system is not just its volume, but its duration. The circulation is incredibly slow, operating on a timescale that transcends human generations. A single drop of water that sinks off the coast of Greenland today begins a voyage that is almost geological in its pacing. It will travel south, mix with the Antarctic circumpolar current, perhaps drift into the Indian or Pacific Oceans, and slowly rise back to the surface through upwelling zones thousands of miles away. By the time that specific volume of water completes the full circuit and returns to the North Atlantic to sink again, approximately 1,000 years will have passed. The water rising to the surface of the Pacific today may have last seen the Arctic sky during the height of the Middle Ages, carrying with it the chemical signatures and temperatures of a bygone era. This ancient journey brings water back to a region defined not by uniformity, but by distinct invisible barriers. If you were to lower a sensor through a crack in the ice at the North Pole, you would discover that the Arctic Ocean is not simply a cold bowl of water. It is a strictly stratified environment, arranged in layers that stack one upon another like a heavy liquid blanket, maintained by delicate balances of density. Deep below the surface, usually starting around 200 meters down, lies a massive volume of water known as the Atlantic layer. This deep water is actually quite warm, retaining the heat it gathered from the Gulf Stream thousands of miles away. It circles the polar basin in a counterclockwise loop, carrying enough thermal energy to melt the entire polar ice cap from beneath if it were ever allowed to rise to the surface. However, the ice remains intact because this warm, salty layer is trapped in the depths, pinned down by a lighter, colder layer above it. This protective shield is called the cold halocline layer. The term halocline is derived from the Greek words for salt and slope, describing a vertical zone in the ocean where salinity changes rapidly with depth. In most of the world's oceans, temperature is the primary factor that decides which water floats and which water sinks. Warm water usually stays on top. But in the Arctic, salt is the master of physics. The water in the halocline is near the freezing point, but it is significantly fresher than the Atlantic water beneath it. Because fresh water is less dense than salt water, this cold, buoyant layer floats on top of the warm, heavy, salty, deep water. It acts as a critical insulator, a lid that prevents the ocean's stored heat from escaping upward to attack the sea ice. The source of this buoyancy is a relentless influx of fresh water from the surrounding continents. The great rivers of Siberia and North America, the Ob, the Yenisei, the Lena, and the Mackenzie, drain vast portions of the northern hemisphere directly into the Arctic basin. These rivers pour thousands of cubic kilometers of fresh water into the ocean every year. This massive volume of river runoff mixes with the surface water, lowering its salinity and reinforcing the barrier that keeps the warm Atlantic water safely submerged. Pacific water also enters through the narrow Bering Strait, adding another distinct layer of fresher, nutrient-rich water that slides between the surface and the deep Atlantic pool. This complex stratification creates a unique hydrographic structure where the water actually gets warmer as you go deeper, a phenomenon known as an inverted temperature profile. The stability of the North Pole's ice cover depends entirely on this stratification remaining undisturbed. This structuring of the water column does more than just preserve the physical ice. It organizes the biological world. The layers create specific habitats, like floors in a building, where different organisms have adapted to precise conditions of pressure, light, and salinity. In the boundary layers where waters of different densities meet, microscopic life forms often accumulate, suspended in the density gradients. Yet perhaps the most fascinating habitat lies not in the open water, but within the solid ceiling above it. To the naked eye, the sea ice at the North Pole appears to be a stark, monolithic slab of frozen white material. Under microscopic examination, however, sea ice reveals itself to be a complex, porous matrix, more akin to a rigid sponge or a honeycomb than a solid block of glass. When ocean water freezes, the ice crystal structure pushes out the dissolved salt, a process known as brine rejection. This concentrated salty liquid becomes trapped in a labyrinth of microscopic veins and pockets known as brine channels. These channels remain liquid even when the surrounding temperature drops well below the freezing point of fresh water, creating a sanctuary for life. Inside these tiny hypersaline tunnels, a specialized community of microorganisms thrives, dominated by ice algae and pinnate diatoms. These are not ordinary plants. To survive here, they have evolved biological mechanisms that rival the most advanced engineering. They produce cryoprotectants, special sugars and lipids that prevent jagged ice crystals from forming inside their cells and rupturing their membranes. They also modify the fatty acids in their cell walls to remain fluid and flexible when other oils would turn into hard wax. For months, these microscopic tenants wait in the crushing darkness of the polar winter. They exist in a state of suspended animation, conserving energy until the first rays of the sun return in spring. When the light finally pierces the snow cover, the reaction is explosive. The diatoms begin to photosynthesize rapidly, creating a bloom so dense that it physically changes the color of the ice. If you were a diver looking up at the underside of the floes during this season, you would not see a white sheet, but rather vast shades of golden brown and green. Scientists often refer to this phenomenon as an upside-down pasture. This inverted meadow serves as the critical nursery and grazing ground for the entire Arctic ecosystem. Tiny grazers, such as amphipods and copepods, migrate to the undersurface of the ice to feed on this algal mat. These small crustaceans use specialized appendages to scrape the algae from the ice, consuming the energy-rich fats produced by the diatoms. This is the absolute foundation of the food web. The distinct omega-3 fatty acids created by these microscopic ice dwellers eventually fuel the ringed seal, the Arctic cod, and ultimately the massive polar bear. Without the bloom in the brine channels, the apex predators would effectively starve. As the summer warmth increases and the ice begins to melt, this upside-down pasture detaches and sinks. It falls through the water column as distinct clumps of biological material, often called marine snow, delivering a massive pulse of nutrients to the creatures dwelling on the dark seafloor thousands of meters below. Before those sinking clumps of marine snow reach the abyssal plain, many are intercepted by the true engine of the Arctic ecosystem. Suspended in the freezing water column are trillions of tiny crustaceans known as copepods. While they exist in oceans worldwide, the species found near the North Pole have evolved to be significantly larger and richer in energy than their tropical counterparts. If you were to look closely at a single copepod, you would see a translucent, teardrop-shaped body propelled by twitching legs and guided by long, sweeping antennae that sense the slightest vibration in the water. These tiny creatures are often described by marine biologists as the butter of the sea. This is because of their remarkable ability to convert the energy from ice algae into pure fat. During the short, explosive bloom of spring and summer, copepods graze constantly, filling lipid sacs within their bodies until fat accounts for more than half of their dry weight. These high-energy wax esters are not just fuel for the copepods to survive the long, dark winter. They are the primary caloric source for nearly every larger animal in the high north. Without these lipid-rich drifting snacks, the bowhead whale, the ringed seal, and the polar cod could not exist. Their movement patterns are just as fascinating as their biology. Copepods perform what scientists call diel vertical migration. It is the largest synchronized movement of biomass on the planet, occurring every single day. In lower latitudes, they sink into the dark depths during the day to hide from predators and rise to the surface at night to feed. In the high Arctic, where day and night can last for months, this rhythm shifts. They must carefully time their ascent to match periods of low light, navigating a world of perpetual twilight during the shoulder seasons to avoid visual hunters. Thinking about these extreme shifts between total darkness and constant sunlight brings up a question about our own rhythms. When you think about the changing seasons, do you find yourself preferring the cozy, quiet introspection of winter, or do you feel more at ease during the bright, energetic days of summer? Regardless of the season, the copepods are never alone. Swarming alongside them are krill, slightly larger shrimp-like animals that form dense clouds in the water. Arctic krill are capable of spontaneous bioluminescence, creating faint glimmers in the deep polar night. Then there are the amphipods, creatures that look somewhat like sandhoppers. In the central Arctic, amphipods have a unique lifestyle. They spend much of their lives upside down, walking along the underside of the ice sea. They treat the bottom of the ice like a ceiling, grazing on the algae mats we discussed earlier. This upside-down existence allows them to act as a crucial link, transferring energy directly from the ice surface into the water column below, ensuring that even in the coldest waters, the flow of energy never truly stops. As that energy descends, it eventually reaches the domain of the true giants of these freezing waters. We often imagine the Arctic deep as a barren void, yet the cold depths harbor the lion's mane jellyfish, the largest species of jelly in existence. While the blue whale is famously massive, the lion's mane challenges it for the title of the longest animal on Earth. In these nutrient-rich polar waters, their hair-like tentacles can extend more than 100 feet, trailing behind a bell that pulses with a deep crimson or purple hue. It creates a vast, silent trap, drifting through the currents like a wandering galaxy of stinging threads. This immense size is made possible by the unique chemistry of the pole. A phenomenon known as polar gigantism suggests that the high oxygen content of cold water, combined with significantly slower metabolic rates, allows invertebrates to grow far larger here than their tropical cousins. Because the water is so cold, often hovering just below freezing without turning to solid ice due to the salt content, it becomes more viscous. This slight thickness supports their heavy, gelatinous bodies, allowing them to float with minimal exertion. They do not need to hunt aggressively. They simply exist, relying on the slow, inevitable drift of the ocean to bring food to them. Among these giants float the comb jellies, or ctenophores. These are delicate, translucent orbs that look like glass sculptures. Unlike the lion's mane, they do not sting. If you were to shine a light into the black water, you would see rows of tiny cilia beating rhythmically along their sides to propel them. This movement refracts light, sending shimmering waves of rainbow colors rippling down their transparent bodies, a silent, hypnotic light show in the absolute darkness. Some Arctic ctenophores, like the predatory berry, are bioluminescent, generating their own soft blue-green glow to startle predators or attract mates. It creates a surreal juxtaposition in this environment. The North Pole is defined by its hardness, the crushing pressure of the deep, the jagged solidity of the pack ice, and the biting wind above. Yet the dominant life forms in the water column are defined by their extreme fragility. These animals are more than 95% water, structured only by the liquid around them. They survive not by fighting the harshness of the pole, but by becoming one with its slow, cold rhythm. Moving through this suspended world is a small, silvery fish that serves as the biological foundation for the entire high Arctic. This is the Arctic cod, also known as the polar cod. To the casual observer, it appears modest, rarely growing larger than 30 centimeters in length. It possesses large eyes and a slender, tapered body that shimmers with a faint iridescence. Yet, despite its diminutive size, biologists regard this single species as the keystone of the northern polar ecosystem. Without it, the energy harvested from the sun by microscopic algae would never reach the massive marine mammals that patrol the pack ice. Living here requires a mastery of cold that goes beyond simple endurance. The water temperature near the North Pole frequently drops to nearly 2 degrees below 0 Celsius, the freezing point of seawater. For most vertebrates, this environment is deadly. The salt content in a typical fish's blood is lower than that of the surrounding ocean, meaning their fluids should theoretically freeze at roughly negative 0.5 degrees. In the high Arctic, the ocean is significantly colder than the freezing point of the fish's own blood. By all laws of thermodynamics, the Arctic cod should turn into a solid block of ice. It survives thanks to a remarkable evolutionary innovation circulating within its veins. The liver of the Arctic cod produces specialized antifreeze glycoproteins. These are not simple sugars, but complex molecules designed with a specific architectural purpose. When microscopic ice crystals begin to form within the fish's body, a process that would normally rupture cells and cause death, these proteins identify the emerging crystal lattice. They physically bind to the surface of the ice crystal, effectively wrapping it in a chemical blanket. This binding prevents other water molecules from joining the crystal structure, halting its growth instantly. This allows the cod to swim through supercooled waters that remain technically below the freezing point of its own tissues, surviving in a state that defies the standard rules of biology. This adaptation allows them to inhabit a world where few competitors can follow. They do not merely swim beneath the ice, they inhabit its complex underbelly. The bottom of sea ice is not a flat sheet, but a jagged, upside-down landscape of ridges, caves, and crevices. Arctic cod are frequently observed swimming upside down, skimming the ceiling of the ocean, tucking their bodies into fissures in the ice to hide from predators. In these frozen sanctuaries, they feast on copepods and amphipods, the tiny crustaceans that graze on the algae growing on the ice itself. This diet transforms the cod into a vital energy conduit. They concentrate the low-density calories of the plankton into rich, dense reserves of fat. When a ringed seal, a narwhal, or a beluga whale hunts in these waters, they are dependent on the Arctic cod to access the energy produced by the microscopic world. It is estimated that in some parts of the high Arctic, this single fish species accounts for 75% of the energy transfer from plankton to warm-blooded animals. They move in swarms of staggering magnitude, sometimes numbering in the hundreds of millions, forming a living, shifting layer of biomass that flows silently through the dark waters of carrying the heat of life through the coldest ocean on Earth. Beneath these swarming schools, drifting in the abyssal gloom, there exists a predator that operates on a timescale almost incomprehensible to the human mind. The Greenland shark moves through the deep Arctic waters with a lethargy that defies our standard understanding of hunting. They are often called sleeper sharks because of their sluggish, almost trance-like behavior. While most sharks are defined by their speed and aggression, the Greenland shark cruises at an average pace of less than 1 mile per hour, making it the slowest swimming shark species in the world. Its tail sweeps back and forth in a languid rhythm that barely disturbs the water, conserving every possible calorie in an environment where energy is a precious commodity. This extreme slowness is the external symptom of a metabolism that runs at the very edge of stasis. In the freezing depths, chemical reactions within the body slow down, and this physiological braking mechanism has granted the Greenland shark a lifespan that seems closer to science fiction than biology. By analyzing the radiocarbon found in the nuclei of their eye lenses, tissue that forms before birth and never changes, scientists have determined that these animals are the longest living vertebrates on Earth. Current estimates suggest they can live at least 400 years, with some individuals potentially reaching 5 centuries of age. To put this into perspective, a large female swimming beneath the ice today could have been born while the Ming Dynasty still ruled China, or before the ink was dry on the plays of Shakespeare. They are living time capsules, silent witnesses to history that have been patrolling the dark while the entire modern world was built above the surface. Perhaps the most staggering fact about their longevity is the timeline of their development. In a world where many creatures live and die within a single season, the Greenland shark does not even reach sexual maturity until it is approximately 150 years old. Imagine a childhood that lasts for a century and a half. A shark born during the American Civil War would only now be entering adulthood, finally ready to contribute to the next generation. This incredibly delayed maturity makes their population fragile, as they must survive the hazards of the ocean for 15 decades before they can reproduce. If you were to encounter one of these ancient giants in the dark, you might notice a milky cloudiness in their eyes. The majority of Greenland sharks are functionally blind. They are the specific hosts for a parasitic copepod called Omatokita elongata, a small worm-like crustacean that attaches itself permanently to the shark's cornea. The parasite feeds on the eye tissue, destroying the shark's vision and often dangling from the eye socket like a grotesque tassel. However, in the pitch black of the deep polar ocean, sight is largely unnecessary. The shark relies instead on a highly developed olfactory system. Its brain is dominated by the olfactory bulb, allowing it to detect the scent of decaying matter from miles away. They are the scavengers of the pole, cleaning up the biological debris that falls from the surface. You might wonder how such a slow, blind creature has survived for millions of years without being hunted to extinction by faster predators or humans. The answer lies in their biochemistry. The flesh of the Greenland shark is toxic. To prevent their bodies from freezing solid in the sub-zero temperatures or collapsing under the immense water pressure, their tissues are saturated with high concentrations of urea and trimethylene oxide. This chemical cocktail acts as a potent natural antifreeze, stabilizing their proteins against the cold. However, it also means their meat is poisonous to most animals. If eaten raw, the high urea content breaks down into ammonia, causing a state of severe intoxication and neurotoxic effects similar to extreme drunkenness. This natural chemical defense has allowed them to drift, undisturbed and uneaten, through the centuries. While the Greenland shark relies on hidden toxicity for safety, the narwhal relies on an exquisite sensitivity to the ice itself. Often called the unicorn of the sea, this medium-sized whale is instantly recognizable by the long, spiraling tusk protruding from its head, a feature that has fueled mythology for thousands of years. But the biological reality of this structure is far more complex than a simple horn. The tusk is actually an enlarged canine tooth, usually the left one, which grows right through the animal's upper lip. It spirals in a consistent counterclockwise direction and can reach lengths of over 9 feet. For centuries, biologists debated the function of this ivory spear, assuming it was a weapon used for fighting rivals, or perhaps a tool for breaking through ice crusts. While males do cross tusks during social interactions, recent research has revealed that the tusk is primarily a sensory organ with unparalleled receptivity. Unlike human teeth, which have a hard enamel exterior protecting the sensitive nerves inside, the narwhal tusk is built effectively inside out. The hard, protective material is in the center, while the outer layer is porous and permeable. Electromicroscopy has shown that the surface of the tusk is riddled with millions of microscopic tubules that allow seawater to enter and contact the nerve endings directly. This connects the ocean environment straight to the narwhal's brain. It functions as a sophisticated sensor capable of detecting subtle changes in water temperature and pressure. Perhaps most importantly, it detects salinity gradients. When sea ice begins to form, salt is expelled from the freezing water, creating a brine that increases the salinity of the surrounding ocean. By tasting this chemical shift, the narwhal can effectively sense the formation of ice before it happens, allowing them to navigate the freezing labyrinth of the Arctic winter and avoid becoming trapped. This sensory guidance is critical because narwhals are creatures of the deep abyss. During the winter months in Baffin Bay, they perform some of the deepest dives of any marine mammal, regularly descending over 1.5 kilometers into the pitch-black depths. That is nearly a mile of water above them, creating pressure exceeding 150 atmospheres. To survive this crushing weight, their physiology has diverged significantly from surface-dwelling mammals. Their rib cages are compressible and flexible. Instead of resisting the pressure, the ribs fold inward, allowing the lungs to collapse safely without snapping bones or rupturing tissue. They do not carry oxygen in their lungs during these dives. Instead, they store it in their muscles. Their tissue is packed with extremely high concentrations of myoglobin, the protein that binds oxygen, rendering their meat nearly black in color. This allows them to hunt for Greenland halibut on the sea floor for 25 minutes at a time without taking a breath. Yet they must eventually return to the surface, and this is where their specific evolution meets the geology of the North Pole. The surface of their world is a solid ceiling of shifting pack ice. Narwhals are dependent on leads, cracks, and fractures in the ice flows to access the air. Because the ice is constantly moving, driven by wind and currents, these breathing holes can open and close unpredictably. To navigate this dangerous ceiling, the narwhal lacks a feature common to almost all other whales, the dorsal fin. A fin on the back would be a severe liability in the frozen north, preventing the whale from surfacing in small cracks or causing injury when swimming close to the jagged underside of the ice. Instead, they possess a low, tough dorsal ridge that allows them to slide effortlessly beneath the frozen canopy. To break through that canopy, the bowhead relies on a skeletal adaptation that acts as a biological battering ram. The whale's skull is immense, occupying nearly 1/3 of its total body length, and is shaped like a giant reinforced triangle. The bone at the crown of the head is exceptionally dense, designed to withstand the violent impact of colliding with a solid ceiling. When a bowhead needs to breathe and finds itself trapped beneath a continuous sheet of ice, it does not retreat. Instead, it rises vertically, driving the peak of its skull upward with tremendous force. Researchers have documented these whales shattering sea ice up to 60 centimeters or 2 feet thick to create their own breathing holes. This structural resilience grants them access to high-latitude areas of the Arctic that remain closed off to other cetaceans, who would drown beneath the unyielding surface without pre-existing gaps. Survival in these frozen, ice-choked waters requires more than just a heavy skull. It demands the ultimate form of thermal protection. Here, the bowhead possesses a physiological advantage that remains unrivaled in the animal kingdom. It carries the thickest layer of blubber of any whale, a dense mantle of fat that can exceed 50 centimeters, or roughly 20 inches in depth. Unlike the thinner layers found on faster-moving rorquals like the blue whale, the bowhead's insulation is so substantial that it renders the animal positively buoyant. They do not need to actively swim to stay afloat. They can simply rest at the surface, bobbing like a cork. This immense coating acts as a thermal fortress, preserving internal heat so efficiently that the whale maintains a stable mammalian body temperature even when submerged in polar water that hovers near the freezing point of salt water. This highly efficient retention of heat and energy supports a lifespan that challenges the limits of biology. For decades, marine biologists assumed bowhead whales had lifespans similar to other large mammals, perhaps 60 or 70 years. However, a startling discovery in 2007 radically shifted this timeline. A bowhead whale recovered off the coast of Alaska was found to have a foreign object embedded deep within its neck muscle. Upon extraction and analysis, historians identified the object as a fragment of a bomb lance, a specific type of explosive harpoon manufactured in New Bedford, Massachusetts. The patent and manufacture date of the weapon revealed that it was made in the late 1800s. This particular whale had survived a Victorian-era hunt and continued to swim the Arctic waters for another 150 years. Subsequent chemical analysis of the amino acids in bowhead eye lenses has confirmed that they can live well over 200 years, making them the longest-lived mammals on Earth. There are likely individuals swimming in the North Pole today that were born before the Industrial Revolution began to alter the climate of their home. Living in the perpetual twilight of the polar winter, often under heavy ice, limits the utility of vision, so these ancient giants rely on a sophisticated acoustic world. The Arctic is surprisingly noisy. The grinding, cracking, and shifting of ice floes creates a cacophony of background static. To communicate through this interference, bowheads utilize a vocal repertoire that is distinctly different from the repetitive, haunting melodies of the humpback whale. Scientists have described bowhead vocalizations as jazz-like in their complexity. Their songs are free-form and highly variable, consisting of hundreds of distinct sounds that they seem to improvise and alter constantly, allowing them to coordinate their movements through the shifting labyrinth of the polar ice pack. Moving through that same frozen maze is a creature that seems to have been sculpted directly from the ice itself. The beluga whale is perhaps the most instantly recognizable resident of the Arctic, yet it has evolved specifically to disappear. While most cetaceans feature dark backs to blend in with the deep ocean water when viewed from above, the beluga is entirely white. This lack of pigmentation provides exceptional camouflage amidst the floating sea ice, allowing them to swim undetected by visual predators like killer whales. Interestingly, this spectral white color is a sign of maturity. Beluga calves are born a dark, smoky gray or brown, only fading to that characteristic snowy white as they reach adulthood, a process that can take up to 8 years to complete. Their adaptation to the ice goes beyond mere color. If you were to watch a beluga swimming, you might notice a movement that looks startlingly unnatural for a whale. It can turn its head. In almost all other cetaceans, the 7 neck vertebrae are fused together to provide stability for high-speed swimming, locking the head in a fixed position relative to the body. The beluga, however, retains 7 distinct unfused vertebrae. This anatomical flexibility allows them to nod and turn their heads side to side with a range of motions similar to a human's. This is not just for social expression, it is a critical survival tool in the frozen north. By craning their necks, belugas can scan the underside of the ice sheet above them, visually searching for small pockets of air or cracks where they might surface to breathe. It also aids them in hunting on the ocean floor, where they can maneuver their heads to root out crustaceans and fish hiding in the sediment. While their eyes are scanning the ice, their world is primarily defined by sound. Belugas are frequently called the canaries of the sea, a nickname earned by their high-pitched chirping vocalizations that can often be heard above the water by sailors and researchers. Their physical mechanism for this projection is the large, bulbous forehead known as the melon. Unlike the solid structures in other whales, the beluga's melon consists of fatty tissue that is malleable. They can physically alter the shape of their forehead by blowing air around their sinuses, which focuses their echolocation clicks into a directional beam. This allows them to see through the dark, murky Arctic waters with astonishing precision, identifying the thickness of ice layers or the presence of prey at great distances. As the seasons shift and the ice retreats, these white whales engage in a physiological ritual unique among cetaceans, a seasonal molt. Most whales shed their skin continuously and imperceptibly, sloughing off dead cells much like humans do. Belugans, however, shed their entire outer layer of skin all at once during the summer. To facilitate this, they migrate into warmer, shallow freshwater estuaries. The warmer water temperature is thought to accelerate their metabolism and encourage blood flow to the cutaneous layers, which is usually restricted in freezing deep ocean to conserve heat. In these shallow river mouths, thousands of belugas can be found rolling and rubbing their bodies against the coarse gravel of the riverbeds, physically scraping away the old yellowed epidermis to reveal the fresh, bright white skin underneath. Yet, even as they rejuvenate their skin in the shallows or navigate the deep ice channels. They are constantly monitored. The very breathing holes that sustain them in the winter pack ice can become perilous traps if the freeze happens too quickly. While the water offers them three-dimensional freedom, the surface is a two-dimensional boundary where a different kind of hunter waits patiently for the sound of a blowhole breaking the silence. That patient hunter is the polar bear, an apex predator that has mastered the art of living on the knife edge between solid and liquid. While we typically visualize bears as terrestrial creatures roaming the forests and mountains of the temperate world, scientists classify the polar bear quite differently. They are designated as marine mammals, the only bear species to hold this title. Their scientific name, Ursus maritimus, literally translates to sea bear, grouping them ecologically with whales, seals, and walruses rather than their cousins in the wooded south. This classification is not merely a technicality. It reflects a biological reality where the ocean provides their primary habitat, their food source, and the platform upon which they travel. To understand how a land mammal came to conquer the frozen ocean, we must look back into the genetic history of the Pleistocene epoch. Genetic studies suggest that polar bears diverged from a population of brown bears relatively recently in geological terms, perhaps as recently as 150,000 years ago. During a period of intense glaciation, a group of brown bears became isolated in the high latitudes. Over generations, the unforgiving selection pressures of the Arctic forced a rapid evolutionary transformation. They did not just change their behavior, they fundamentally altered their physiology to survive in a world where the ground itself is transient ice. One of the most sophisticated adaptations resulting from this divergence is their coat, which appears stark white to the human eye, blending perfectly with the snow and ice pack. However, this whiteness is an optical illusion of physics. Each individual hair of a polar bear is actually transparent and pigment-free. Each shaft is hollow, acting somewhat like a tiny fiber optic cable. When sunlight hits the fur, the light is scattered and reflected by the complex structure of the hollow core, creating the appearance of bright white luminescence. But this structure serves a thermal purpose beyond camouflage. It allows solar radiation to penetrate through the thick coat down to the skin. Here lies another contradiction. The skin of a polar bear is jet black. This dark pigmentation allows them to absorb and retain whatever heat manages to filter through the fur, a critical advantage in an environment where winter temperatures frequently drop to 40 degrees below zero. Because their habitat is often fractured by leads of open water, the polar bear has evolved into a swimmer of startling endurance. While a human might struggle to last minutes in the freezing Arctic Ocean due to cold shock, polar bears are insulated by a layer of blubber up to 4 inches thick, which provides both warmth and buoyancy. They have been tracked swimming continuously for days at a time without resting on solid ground. In one recorded instance, a female bear swam for 9 days straight, covering a distance of over 400 miles. Their large front paws, which can measure up to 12 inches across, are slightly webbed and act as powerful oars to propel them through the water, while their hind legs serve as rudders for steering. Despite their prowess in the water, they are not aquatic hunters like sharks. They are ice hunters who use the frozen surface as a platform. Their primary method of securing food relies on a strategy known as still hunting. The bear locates a seal's breathing hole, a small maintained opening in the ice, and simply waits. This vigil requires a stillness that seems almost inorganic. A bear might stand or lie motionless for hours or even days, ignoring the biting wind and drifting snow, waiting for the singular moment a seal surfaces to breathe. When the seal exhales, the bear detects the disturbance and strikes with lightning speed, pulling the prey up onto the ice. This hunting style depends entirely on an olfactory system that borders on the supernatural. The polar bear possesses one of the most acute senses of smell in the animal kingdom, capable of perceiving the world through a chemical map invisible to us. They can detect the scent of a seal from 20 miles away, or pinpoint a breathing hole covered with 3 feet of compacted snow. Inside their long snout, the surface area of the nasal turbulence bones is immense, lined with millions of scent receptors that constantly analyze the composition of the Arctic wind. The chemical signature dominating that wind usually belongs to the ringed seal, the fundamental cornerstone of the high Arctic food web. While they are the smallest of the northern seals, rarely exceeding 150 pounds, they are also the most abundant, with a population estimated in the millions dispersed across the circumpolar north. Their success lies in a specific adaptation that allows them to inhabit the solid, land-fast ice long after other species have been forced to retreat to the open water at the flow edge. As winter deepens and the ocean surface freezes into a solid sheet, sometimes reaching 6 feet in thickness, the ringed seal does not migrate. Instead, it maintains a series of breathing holes, technically known as oglu, by physically abrading the ice. They possess remarkably stout, curved claws on their foreflippers, which act as heavy-duty scrapers. It is a labor of constant vigilance. If a seal neglects a hole for even a short period during extreme cold, the sea will reclaim it, freezing the opening shut. To ensure survival, a single seal often maintains 10 or more distinct breathing holes spread over a wide area, offering multiple escape routes and access points to the air. Above these breathing holes, specifically where the ice has buckled to form pressure ridges that catch drifting snow, the female ringed seal constructs a subnivean lair. This is a hidden cave excavated within the snowpack itself, located directly over a breathing hole but completely invisible from the surface. The heat rising from the ocean water and the seal's body helps glaze the interior walls with ice, creating a stable, insulated pocket where temperatures remain significantly warmer than the biting wind outside. Inside this hidden chamber, the pup is born. These pups are coated in a thick layer of white lanugo fur, providing camouflage and warmth, yet they remain vulnerable. While the layer hides them from the eyes of predators, it cannot hide them from the sensitive nose of the polar bear, which can detect the faint scent of the seal wafting through meters of compacted snow. This predation dynamic is driven by thermodynamics. Ringed seals are hunted not merely for sustenance, but for the extreme caloric density. They carry a massive amount of blubber relative to their body size, turning them into swimming energy reserves. For a predator living in a frozen desert, consuming this high-fat blubber is the only way to maintain body temperature. Muscle protein alone would result in a net energy loss. Sharing these waters is the much larger bearded seal, often called the square flipper by locals due to the unique shape of its forelimbs. Weighing up to 3 times as much as a ringed seal, the bearded seal occupies a slightly different niche. It is a benthic feeder, meaning it relies on the seafloor for food. Its most defining feature is a magnificent set of thick, sensitive whiskers, or vibrissae, which curl inward when dry. These are highly innervated tactile sensors, allowing the animal to root through the soft mud of the dark ocean floor to locate clams, shrimp, and crabs. Because they must dive to the bottom to feed, bearded seals generally remain in the shallower waters over the continental shelf, avoiding the abyssal depths of the central Arctic basin, where the bottom is beyond their reach. Sharing these productive, shallow waters over the continental shelf is perhaps the most instantly recognizable giant of the Arctic marine ecosystem, the walrus. Like the bearded seal, the walrus is a benthic feeder, meaning its survival depends entirely on the ability to reach the seafloor. This biological constraint tethers the massive herds to the coastal regions where the water depth does not exceed 80 to 100 meters, keeping them safely within the boundaries of the continental shelf and away from the deep central basin. When a walrus dives into the murky darkness of the seabed, sight is of little use. Instead, they rely on a highly specialized sensory array that defines their appearance. The broad, bristly snout, technically known as the moustachial pad, is covered in 400 to 700 stiff, quill-like whiskers called vibrissae. These are not merely facial hair, but highly innervated tactile organs, rooted in blood-filled sinuses and connected to a massive portion of the animal's brain. In terms of sensitivity, these whiskers are functionally similar to human fingers. A walrus can distinguish between shapes and textures of objects as small as a bead purely by touch, while rooting through the soft sediment in total darkness. Once prey, usually a clam or mussel, is located, the walrus does not crush the shell with its teeth. Instead, it employs a powerful hydraulic technique. By creating a seal with its fleshy lips and retracting its massive tongue like a piston, the walrus generates a vacuum of intense suction, strong enough to rip the soft meat of the mollusk physically out of its shell in a fraction of a second, leaving the intact shells scattered on the ocean floor. While the whiskers serve as the primary foraging tool, the tusks are the walrus's multi-purpose utility instrument. These elongated canine teeth, which can grow to lengths of nearly a meter, are present in both males and females. The scientific name for the walrus, Odobanus rosmarus, translates roughly to tooth-walking seahorse, a nod to one of the tusk's most critical functions. By driving these ivory spikes into the ice, a walrus can haul its immense bulk, often weighing over 1,000 kilograms, out of the freezing water and onto a solid floe. This action is essential for resting, as they are not true aquatic mammals like whales and must return to the surface to breathe and rest. The tusks also serve a social function, acting as visual indicators of dominance and age, minimizing the need for physical conflict within the herd. However, when the water is the preferred resting place, the walrus possesses a remarkable adaptation for sleeping at sea. Located in the neck, specifically in the esophagus, are elastic deviations known as pharyngeal pouches. A walrus can inflate these pouches with roughly 50 liters of air, turning its neck into a biological life jacket. This buoyancy allows the animal to bob vertically in the water column, head held high above the surface, sleeping soundly without treading water or sinking. This ghost-like existence serves them well in their complex relationship with the undisputed apex predator of the region, the polar bear. Arctic foxes often trail polar bears across the sea ice, keeping a respectful distance while waiting for the great white bear to make a kill. Once the bear has eaten its fill of sea blubber and moved on, the fox darts in to scavenge the remains. It is a dangerous strategy, relying on the scraps of giants to survive the leanest months, but it is often the only source of food available on the sterile ice sheet. Thinking about these animals thriving in the biting wind reminds us of our own deep need for warmth. When the weather turns cold where you are, what is your specific comfort ritual? Perhaps it is the weight of a heavy quilt, the steam rising from a hot mug, or simply the feeling of warmth returning to your hands after being out in the wind. For the fox, however, there is no warm room to return to, only the endless expanse of the cryosphere and the clever adaptations that allow life to persist in a freezer. While the fox relies on insulation to endure the winter, the Arctic tern employs a strategy of movement that is unparalleled in the animal kingdom. Rather than bracing against the cold and the dark, this small, elegant bird simply chooses to leave. It initiates a journey that renders the concept of distance almost meaningless. Every year, the Arctic tern flies from its breeding grounds in the high Arctic all the way to the pack ice of Antarctica, and then back again. This is not merely a flight south, it is a global commute from the top of the world to the bottom, holding the record for the longest migration of any animal on Earth. Recent tracking studies using geolocators have revealed that these birds cover an even greater distance than biologists previously estimated. Because they do not fly in a straight line, but rather curve their path to ride prevailing wind systems and preserve energy, a single bird may cover nearly 60,000 miles in a single year. They travel this vast distance to remain in a state of perpetual summer. By chasing the sun across the hemispheres, the Arctic tern sees more daylight than any other creature on the planet. They capitalize on the explosion of marine life that occurs during the polar summers at both ends of the globe, feeding on small fish and crustaceans that thrive in the cold, nutrient-rich waters. The cumulative scale of this travel is difficult to truly comprehend. Arctic terns are surprisingly long-lived for such small birds, often surviving for 30 years or more. When you multiply their annual migration mileage by a lifespan of 3 decades, the arithmetic reveals a staggering fact. In its lifetime, one Arctic tern will fly a distance equivalent to traveling to the moon and back 3 times. They are biological machines built for endurance, navigating the featureless ocean with an internal compass that we are only just beginning to understand. Despite their delicate appearance in the air, with slender pointed wings and forked tails, they are notably fierce when they return to the Arctic tundra to nest. If you were to wander too close to a colony, you would quickly discover their aggressive defense mechanisms. They are known to dive bomb intruders with remarkable speed, striking with their sharp red beaks at the highest point of the threat, which is usually the intruder's head. Even the polar bear, the apex predator of the ice, will often alter its path to avoid the harassment of a nesting colony. This bird serves as a living thread that stitches the planet together, proving that the North Pole is not an isolated point of ice, but part of a continuous loop connected intimately to the frozen continent on the other side of the world. Long before satellite telemetry could track a tern's global flight, the Arctic was a landscape of pure imagination. For thousands of years, the North Pole was not a place humans visited, but a place they invented, filling the blank spaces of their charts with logic, myth, and desire. The earliest written accounts of the far north came from the Greek explorer Pytheas of Massalia, who sailed from the Mediterranean around 325 BC. he ventured far beyond the Pillars of Hercules and the British Isles to a place he famously named Thule. Pytheas returned with descriptions that baffled his contemporaries. He claimed that at the northernmost edge of the world, there was no longer a clear distinction between land, sea, and air. He described a marine lung, a gelatinous suspension binding the elements together, impenetrable by foot or by ship. While later scholars often dismissed him as a fabricator, modern historians suspect he likely encountered the slushy, heaving mix of drift ice and fog that characterizes the panicked boundary of the freezing sea. As the centuries turned and cartography became a formal science, mapmakers could not abide a vacuum at the top of the world. They felt compelled to draw something to explain the physical laws of the planet. In the 16th century, the renowned geographer Gerardus Mercator, whose projection still governs our view of the world, depicted the North Pole with confident precision. He did not draw an ice cap. Instead, he drew a mountain. Mercator's Arctic was dominated by the Rupus nigra, or Black Rock, a massive magnetic island 33 miles in circumference, rising from the center of the pole. This invention solved a critical problem for navigators. It explained why compass needles pointed north. They believed a physical lodestone of immense power must exist to attract the metal. Surrounding this black mountain, maps depicted 4 large continents separated by rushing rivers. It was believed that the oceans of the world poured inward through these channels, disappearing into a giant whirlpool beneath the magnetic mountain to circulate through the center of the Earth. Even as exploration advanced and the magnetic mountain faded from serious thought, it was replaced by an equally dangerous seduction, the theory of the open polar sea. In the 19th century, respected scientists argued that sea ice could only form near land. They theorized that the deep, central Arctic Ocean, bathed in 24 hours of sunlight during the summer, would remain liquid. This thermometric gateway suggested a warm, navigable ocean lay just behind the jagged barrier of coastal pack ice. This belief fueled the desperate obsession with the Northwest Passage. Nations poured fortunes into expeditions, convinced that if a ship could just punch through the outer ring of ice, it would find smooth sailing to the Orient. They did not see the white expanse as a permanent feature, but a temporary gate, guarding a temperate shortcut.
It took centuries of crushed hulls and lost crews to finally erase these invisible mountains and warm oceans, forcing the world to accept the silent, frozen reality that actually lay in wait. By the late 19th century, a Norwegian scientist named Fridtjof Nansen decided to stop fighting this frozen reality and start listening to it. He had noticed something peculiar about the wreckage of previous failed expeditions. Artifacts and debris from a ship crushed near Siberia somehow washed up years later on the coast of Greenland, thousands of miles away. This flotsam suggested that a massive, slow-moving current flowed right across the polar cap, carrying the ice from east to west. Nansen proposed a radical, almost heretical idea. Instead of building a ship to smash through the ice, he would build one designed to be frozen into it. He intended to trap himself in the pack purposefully and let the natural drift carry him across the top of the world. To survive the crushing pressure that had snapped the oak ribs of sturdy whalers like matchsticks, Nansen collaborated with the renowned naval architect Colin Archer. Together, they designed the Fram. The Fram, which means forward, looked unlike any vessel that had sailed before. It was short, wide, and remarkably saucer-shaped, lacking a protruding keel that the ice could grip. The hull was constructed of dense Italian oak, reinforced with iron and insulated with cork, but its true genius lay in its geometry. The theory was simple physics. When the ice pack closed in and squeezed the hull, the rounded bottom would force the ship upward, popping it out of the water to sit safely on top of the ice, like a cherry pit squeezed between two fingers. In 1893, Nansen put this theory to the ultimate test. He sailed the Fram east along the Siberian coast and drove her straight into the pack ice. As the polar night descended and the temperature plummeted, the ice cemented around the hull. The crew waited for the inevitable crushing sound of timber splintering. Instead, they felt the ship groan, shudder, and slowly rise. The design worked perfectly. For the next 3 years, the Fram became a drifting scientific station entirely at the mercy of the current. While the world assumed they were lost, the crew lived in relative comfort, insulated from the -40-degree winds, conducting rigorous oceanographic work. They lowered instruments through holes in the ice to measure sea temperatures and took depth soundings, discovering that the Arctic was not a shallow sea, as previously thought, but a deep ocean basin. The pace of discovery was dictated solely by the slow, grinding movement of the floes. Eventually, realizing the drift would miss the geographic North Pole, Nansen and one companion, Hilmar Johansen, left the safety of the ship to make a dash for the pole on skis and dog sleds. They entered a white void of chaotic pressure ridges and shifting lanes of water. They pushed north for weeks, but the ice beneath them was drifting south, creating a heartbreaking treadmill effect where their progress was constantly erased by the ocean's movement. They reached 86 degrees 14 minutes north, further than any human had ever gone, before prudence forced them to turn back. While they spent a harrowing winter surviving in a stone hut on a remote archipelago, the Fram continued its passive journey. Remarkably, the ship eventually emerged from the ice on the other side of the Atlantic, just as Nansen had predicted. The expedition did not reach the exact mathematical point of the pole, but it revolutionized polar science. It proved the Arctic was a dynamic, moving ocean, not a static continent, and demonstrated that survival there required yielding to the forces of nature rather than trying to conquer them with brute force. But for the explorers at the turn of the 20th century, drifting passively with the ice was not enough. The goal was the precise 90-degree mark, a mathematical abstraction that became the ultimate prize in what was often called the race to the pole. This drive for priority led to one of the most famous and bitter controversies in the history of science. In the autumn of 1909, the world received conflicting telegrams from the far north. First, Frederick Cook claimed to have reached the North Pole in April of 1908. Days later, Robert Peary announced that he had planted his flag there in April of 1909. The ensuing debate divided the public and scientific societies for decades, yet it highlighted a profound difficulty unique to the Arctic environment. Verifying success at the North Pole is fundamentally different from verifying it at the South Pole. Antarctica is a continent. If you leave a flag there or a cairn, it stays there. The North Pole, however, is merely a coordinate on a frozen ocean skin that never stops moving. You're essentially trying to pin down a location on a conveyor belt. Even if an explorer stood at the exact top of the world, the ice beneath their boots might be drifting south at several miles per day. By the time they finished taking a solar observation to confirm their location, the mathematical pole would already be behind them. This made proof notoriously difficult before the age of satellite navigation. Determining one's position relied on the sextant and the chronometer, precision tools that were agonizing to operate with frostbitten fingers in temperatures 40 degrees below zero.
Atmospheric refraction near the horizon could distort calculations, and the constant shifting of the ice pack meant that a team could march north for 10 hours only to find that the southward drift of the currents had negated nearly all their progress. It was a treadmill of ice, demanding not just endurance, but a kind of psychological fortitude that is hard to imagine today. Beyond the mathematics of navigation, the logistics of these early 20th century attempts were staggering. Explorers had to carry tons of supplies, establishing caches along the route, yet every mile north stretched the supply line thinner and more vulnerable. They navigated through a chaotic maze of pressure ridges, walls of ice pushed up by colliding flows, and open leads, which are sudden cracks revealing the dark, deadly ocean below. These water barriers forced days of detours, draining precious food and energy. Because of these navigational ambiguities and the lack of independent witnesses, modern historians still debate the validity of both Cook's and Peary's claims. Many experts now believe that neither man actually reached the precise geographic pole, though they certainly got close enough to experience the full brutality of the high Arctic. It leaves us with a surprising realization. The first undisputed, verified arrival at the North Pole likely did not happen on foot. While the Nautilus passed beneath the ice without stopping, later vessels perfected the art of breaking through it. Modern submarines are designed with reinforced sails, hardened with high-strength steel, allowing them to breach the frozen surface. The maneuver requires finding a polynya, or a patch of thinner ice, using that same upward-looking sonar. The submarine hovers, then creates positive buoyancy to rise vertically, using the sheer upward force of thousands of tons of displacement to fracture the ice. The image of a submarine's black tower erupting through the pristine white snow signaled a shift in polar science, moving from the age of surface exploration to a new era of subsurface mapping, where the true shape of the planet was revealed by sound rather than sight. While the submarine relies on stealth to navigate the underside of the ice cap, the surface vessels designed to conquer the frozen ocean rely on brute force and specific geometry. The physics of an icebreaker are often misunderstood. Despite the name, these ships do not slice through the ice like a knife cutting through a solid sheet. If a ship merely pushed forward against the edge of an ice floe, the immense friction would trap the hull immediately. Instead, an icebreaker functions by converting its forward momentum into downward pressure. The bow is not sharp and vertical like an ocean liner. It is shaped like a spoon, angled gently backward. This design allows the ship to ride up onto the shelf of the ice, beaching its front section. Once the bow is resting on the surface, gravity takes over. The colossal weight of the ship bears down, snapping the ice beneath it, and the vessel falls through the fracture, pushing the debris aside before moving forward to repeat the cycle. This violent process requires an extraordinary resilience. The steel used in polar-class vessels is of a specific metallurgical grade, designed to remain ductile at temperatures where ordinary metal becomes brittle and prone to shattering. At the waterline, the ship is reinforced by an ice belt, a band of extra-thick steel capable of withstanding the crushing lateral pressure of shifting pack ice. In some modern designs, the hull is coated with specialized low-friction paint or even stainless steel to ensure the ice flows smoothly past without adhering to the metal. To further reduce friction, many icebreakers utilize an air bubbling system. Compressed air is pumped out through small holes in the hull below the waterline, creating a rising curtain of bubbles that lubricates the interface between the ship and the frozen ocean, reducing resistance and helping to clear broken chunks from the ship's path. The energy required to constantly drive a 20,000-ton vessel up onto solid ice is immense, which is why the most powerful icebreakers on Earth are nuclear-powered. Russia operates the world's only fleet of nuclear icebreakers, utilizing the Arctica-class vessels to keep the Northern Sea route open. These ships are equipped with dual nuclear reactors that generate steam for massive turbines, providing virtually unlimited range and the torque necessary to churn through ice up to 3 meters thick without pausing. The most recognizable of these giants is perhaps the Yamal, famous for the stylized shark teeth painted on its bow, a visual warning that matches its capability to crush through ridges of multi-year ice. Even with nuclear propulsion, the sensation of breaking ice is intense. For those on board, the experience is never silent. The collision of steel and ice creates a constant, rhythmic grinding sound, a resonant vibration that shudders through the deck plates. When hitting a particularly thick pressure ridge, the ship may come to a halt, requiring the captain to back up and ram the obstacle again, a maneuver known as backing and ramming. To prevent becoming trapped during these pauses, these ships have healing systems, ballast tanks that rapidly pump water from the port side to the starboard side and back again. This shifts the ship's center of gravity, rocking the entire vessel side to side to break the static friction of the ice, ensuring the grip of the North Pole never holds tight enough to keep the ship from moving. As that ship carves its path, leaving a trail of dark water behind it, it is inadvertently demonstrating one of the most critical equations in planetary physics. The stark visual contrast between the brilliant white sea ice and inky black ocean is not merely an aesthetic difference. It is a fundamental difference in energy management. This brings us to the concept of albedo. Derived from the Latin word for whiteness, albus, albedo measures the reflectivity of a surface. It is essentially a score from 0 to 1. A perfectly black surface has an albedo of 0, acting as absorbing every photon that strikes it. A perfectly white surface has an albedo of 1, acting as a flawless mirror. In the context of the global climate system, fresh, clean snow at the North Pole is one of the most reflective natural substances on Earth. It can have an albedo as high as 0.9, meaning it bounces 90% of the sun's incoming heat straight back out into space, away from the planet. It acts as a planetary shield, a giant reflector that helps regulate the temperature of the entire globe. However, the ocean water hidden beneath that ice tells a very different thermal story. Open ocean water is dark. It has a very low albedo, often roughly 0.06. Instead of reflecting the sun's rays, the dark ocean absorbs them. It takes that solar energy and converts it into heat, warming the water layers near the surface. This dynamic creates a sensitive physical relationship known as the ice-albedo feedback loop. It functions like a self-reinforcing cycle. As the air warms, a patch of white ice melts, revealing the dark water beneath. That patch of open water, now exposed to the sun, absorbs far more heat than the ice did. This warms the water further, which eats away at the edges of the remaining ice, causing more melting, revealing more dark water, and absorbing yet more heat. Because the sun does not set at the North Pole for months at a time during the summer, this energy absorption can be continuous, accelerating the retreat of the ice edge. This feedback loop is the primary engine behind a phenomenon scientists call Arctic amplification. It explains why the Arctic tends to warm at a rate significantly faster than the rest of the planet, often estimated to be 2 to 4 times the global average. While the equator dissipates heat through evaporation and storm systems, the North Pole relies heavily on this reflective shield to stay cool.
When the shield weakens, the temperature difference between the pole and the equator shrinks, which can alter global wind patterns in complex ways.
But temperature is not the only variable that affects this reflectivity. The purity of the snow matters. Even at the remote North Pole, the ice is not always pristine white. Atmospheric circulation can carry microscopic particles of dust, ash, and soot, often referred to as black carbon, from wildfires or industrial activity thousands of miles away. When these tiny, dark specks settle on the snow, they lower the albedo. The physics here function on a granular level. A single particle of soot absorbing the sun's warmth heats up faster than the snow crystal it sits upon. It creates a microscopic pocket of meltwater, causing the particle to sink slightly into the snowpack. This does not just melt the snow, it ages it. The snow grains coarsen and clump together. Larger, wetter snow grains are less reflective than fine, dry powder. So even without a massive temperature spike, a dusting of particulate matter can darken the surface enough to accelerate the melting process, turning the bright mirror of the Arctic into a darker, heat-absorbing sponge. This thermal change attacks the structural integrity of the ice itself, creating a critical distinction in the geology of the North that determines how long the ice cap can survive. To understand the fragility of the current landscape, we must distinguish between the two specific classes of frozen water floating on the Arctic Ocean. The first is known as first-year ice. This is the new growth that forms during a single winter season. It is typically thin, usually less than 2 meters deep, and because it freezes rapidly from seawater, it traps pockets of salty brine within its crystal structure. This salt content makes the ice softer and more prone to fracturing when the winds shift. In contrast, the true backbone of the North Pole is multi-year ice. This is the ancient, resilient ice that has survived at least one summer melt season without disappearing. The physics of this survival changes the ice chemically. Over time, gravity pulls the dense, salty brine down through the ice block and back into the ocean, a process known as brine rejection. As the salt drains away, the ice becomes fresher, harder, and much denser. While first-year ice appears opaque and white, multi-year ice often glows with a distinct blue hue and can grow to be 3 or 4 meters thick. It acts as a massive, floating shield, resistant to storms and waves that would easily shatter the younger, thinner layers. The most concerning data from satellite monitoring involves the rapid disappearance of this old ice. 3 decades ago, ice that had persisted for 4 years or more made up a significant portion of the Arctic pack, acting as a stabilizer for the entire region. Today, that old blue ice has dwindled to a tiny fraction of the total area. We are effectively replacing a thick, hardened shield with a thin, brittle skin that breaks apart easily and melts away almost entirely every summer. This thinning trajectory has led climatologists to discuss the probability of an ice-free Arctic summer. It is important to clarify that in scientific terms, ice-free does not mean zero ice. The definition usually refers to the point where sea ice extent drops below 1 million square kilometers. In this scenario, the central Arctic basin would be open water, with only small, stubborn patches of frozen material clinging to the northern coastlines of Greenland and the Canadian archipelago. Such a shift transforms the geography of human movement as drastically as it changes the climate. As the ice retreats, it exposes dark ocean water, which absorbs even more solar energy, accelerating the warming loop. However, it also opens the Northern Sea route. This body of water, hugging the Siberian coast, creates a maritime highway that significantly shortens the distance between European and Asian ports compared to the route through the Suez Canal. What was once a frozen barrier, impassable to all but the most powerful nuclear icebreakers, is becoming a navigable ocean for commercial vessels during the warmer months. Imagine the view from the deck of one of these future vessels crossing the pole. I'm curious, if you found yourself on a quiet ship floating at the exact top of the world, would you spend your time gazing up at the rare, piercing starlight or looking down into the deep, dark polar ocean? Let me know which view you find more soothing. The opening of these waters brings the heavy hum of engines into a soundscape that has been silent for millennia. This industrial encroachment highlights the fragility of the system, yet the North Pole persists as the Earth's primary cooling mechanism. It acts as a global thermostat, a massive white reflector that bounces incoming solar radiation back into space, preventing the planet from overheating. This simple physical property, the whiteness of the ice, is responsible for moderating the climate of continents thousands of miles away. The temperature gradient between this frozen axis and the warm equator is the engine that drives the jet stream, steering the storms and weather patterns that water the world's crops and fill its reservoirs. It is a reminder of how deeply interconnected our biosphere truly is. The water freezing at the surface tonight, expelling its salt and sinking into the dark abyss, initiates a slow, majestic current that will travel the globe for centuries. A single drop of water starting its journey here might not see the surface again until it reaches the Indian Ocean or the Pacific, carrying nutrients and oxygen through the deep. The ice is not a static cap, but a dynamic, breathing entity that inhales and exhales with the seasons, growing in the polar night and retreating in the polar day. There is a stark, terrifying beauty in this efficiency. It is an environment of absolutes: absolute cold, absolute wind, and for half the year, absolute darkness. Yet, under that darkness, the magnetosphere funnels solar particles into curtains of green and purple light, the aurora borealis, dancing over a landscape that looks much as it did during the last ice age. It is a place that demands respect, a landscape that has claimed explorers and ships, keeping its secrets buried under meters of drift. As we conclude our expedition to the geographic top of the world, the silence of the high Arctic offers a final, heavy blanket of calm. The wind slows and the great white expanse settles into stillness. If you found value in this exploration of the frozen North and wish to continue learning while you rest, please consider subscribing to the channel to support future documentaries. The North Pole stands as a silent sentinel at the axis of our rotation, a mysterious and vital crown of ice that spins endlessly in the dark, preserving the delicate balance of the world below.